Hi, today I'm going to be showing you how to do a BC FRQ problem. Today we're going to be doing one from 1999 and we're going to be doing number 1. So in this question they give you sort of the prompt is a particle moves in the xy plane so its position at any time t from 0 to pi is given by x of t equals t squared over 2 minus the natural log of 1 plus t and y of t equals 3 sine t. So if we look at A of this problem, it says sketch the path of the particle in the xy plane below and indicate the direction of motion along the path. So to do this, we're going to plug in different t values and find the corresponding x and y values and then plot them on this graph. So to do this, the easiest way that I find is to make a chart. So I'm going to make a chart of t, x, and y values. So I'm going to call this t, x, and y. So if we look at this interval, it's from 0 to pi, so we want our first point to be 0 and our last point to be pi, and then I'll just pick a few points in between so that we can get the general idea of how the curve is moving. So I'm going to choose 0, 0.5, 1, 2, 3, and pi. So you just want to make sure you get your endpoints in there so that you can see where it goes. Okay, so to solve for the x and y coordinates of each of these t values, you basically just plug them into the equations that are given above. So for example, for 0, you would plug 0 into the equation for x, which would be 0 over 2 minus the natural log of 1, and then that ends up being 0. And then over here, you would do 3 times sine of 0, which is also 0. So you can just use your calculator to plug in these different values into the x and y functions and then just figure out what the x and y coordinates will be. So for 0.5, you get that x equals negative 0.28, and for y, you get 1.44. For 1, you get negative 0.19, and for y, you get 2.5. For 2, you get 0.9 and 2.73. For 3, you get 3.11 and 0.42. And for our last point, pi, we get 3.5 and 0. So now you know your x and y coordinates for 6 different points on this graph, and then you can easily plot it and connect the dots to see how it moves. So you should know how to plot simple xy coordinates, so we'll start with 0, 0. And then we have negative 0.28 and 1.44, so it'll be approximately there, and then 1.44. And then we have negative 0.19 and 2.5. And then we have 0.9, that's the x coordinate, and 2.73. And then we have 3.11, 1, 2, 3, and 0.42, and then 3.5, we have it at 0. So as you can see, it's forming kind of a curve like this, so we can go ahead and connect those points. And you can see that this is your graph. Now, also in this equation, they ask you to indicate the direction of motion along the path. So basically, you want to point the direction as t increases. So when t is a low value, such as 0, it's starting here, and as t increases, it moves this way. And then you end up at the maximum of t, which is pi. So you know that the graph is going to be moving that way. And there you have it. You have your graph for x and y and using this parametric function. Okay, so in the next part of this problem, they ask for what value of t does x of t attain its minimum value, and then they ask you to find the xy coordinate at this point. So to find a minimum value, you need to solve for the extrema of this parametric equation. So you can do that by setting the derivative equal to 0. So to first set the derivative equal to 0, we need to find the derivative of x of t. So if you know that x of t equals t squared over 2 minus the natural log of 1 plus t, you can easily find that the derivative of x of t is t, and then we use chain rule here, minus 1 over 1 plus t. So now in order to if we set this equal to 0, we can find the extrema of this parametric equation. So if we make this equal to 0, and now we can multiply by 1 plus t to make this an easier form to solve. So then we would get t squared plus t minus 1 equals 0. So unfortunately you can't factor this, so now we need to remember our quadratic formula and we can use that to solve this, or you could just plug it into your calculator. So when we use the quadratic equation, we find that t equals negative 1 plus or minus the square root of 5 over 2. So if we remember the bounds of t, it can only be between 0 and pi. So if you were to use the minus root 5, you would get a negative number. So we know we can't do that. So we eliminate that option, and we get t equals negative 1 plus root 5 over 2. And then you solve for that, and that equals 0.618. So now you know that the slope of the graph is 0 when t is at 0.618. So this might be a minimum or a maximum. So in order to test for this, we remember the values that we tested in our first part of the problem in part A when we made the graph. So if you remember, when t equals, so we want to check the endpoints to see how this relates to the endpoints. So when t equals 0.618, we get that x of 0.618. When we plug it back into the equation, that equals negative 0.29. Now, if we remember from the previous part of the problem, we knew that x of 0 equals 0 and x of pi equals 3.11. So as you can see here, negative 0.29 is less than 0 and 3.11. So they might try to trip you up by giving you endpoints that are lower than what appears to be the minimum. So just in case, you always want to check these endpoints and make sure that the value that you solve for is less than both of them. So now that we know that negative 0.29 is less than 0 and 3.11, we can safely say that this is a minimum. So now that we know that x is at a minimum when t equals 0.618, and the x value at that point is negative 0.29. So to solve for the x and y points at this time, we already solved for x, so we know that that's negative 0.29. And to solve for y, we simply plug it back into the initial equation. So we get y of 0.618, and when we plug in 0.618 for t, we get that equals 1.738. So now we know that the coordinate at this point is negative 0.29 and 1.738. So in part 3, or part C of this question, they ask you at what time t is the particle on the y-axis. So to find when the particle is on the y-axis, you set x equal to 0. So we know that x of t equals t squared over 2 minus the natural log of 1 plus t. So when we set this equal to 0, you can just plug that into your calculator and you find that t equals 1.285. So now that we know the t value when x equals 0, that's basically the answer to this. So now you know at time equals 1.285, the particle's on the y-axis. So to find the speed and acceleration vector at this time, we need to remember what speed and acceleration are. So you should know that speed is equivalent to the square root of x prime of t squared, or x prime of t squared, plus y prime of t squared. So to solve for this, we need to find x prime and y prime of this parametric equation. So to derive x, so you know x prime of t, it derives simply, so you get t minus, and use chain rule, over 1 plus t. And then for y prime, you know that the derivative of sine is cosine, so that equals 3 times cosine t. So now we can plug these into the speed equation using the value of t to solve for speed. So basically we get speed equals the square root of x prime of 1.285 squared plus y prime of 1.285 squared. So now when we plug in the values of x prime and y prime and t, you get that speed equals 1.196. So there you have it, that's your speed of the particle at this point. Now for acceleration, you know that the first derivative of position is velocity, so that means that the second derivative is acceleration. So basically we need to solve for x double prime and y double prime. So if we already know that x prime of t equals t minus 1 over 1 plus t, we can solve for x double prime of t equals 1 minus 1 over 1 plus t squared using chain rule again. And then if you solve for y double prime, you know that the derivative of cosine t is negative sine t, so you get negative 3 sine t. So now we know that the acceleration vector is basically x double prime of t and y double prime of t. So now we can plug in this t value and solve for the acceleration vector. So if you plug 1.285 into x double prime, you get 1.191. And when you plug 1.285 into y double prime, you get negative 2.879. So there you have it, that's your acceleration vector.